Hey guys, welcome to our final lecture in Calculus 1. So this week we are going to go backwards a little bit, kind of but not really. We're going to talk about more real-world applications to what we've been learning in terms of derivatives and integration. So we're going to go back to what the relationship is between position versus time, velocity versus time, and acceleration versus time. We're going to go back to that relationship, and then since we have a tool to sort of go backwards in a way, what we're going to be looking at is we're going to be looking at velocity graphs, and we're going to be determining information about position or displacement. By using the fact that, velocity is the derivative of position. And so position is the antiderivative of velocity. All right. So we're going to, really look at that a little bit more closely. Then we're going to talk about the fundamental theorem and interpretations in terms of units and why the fundamental theorem of calculus makes sense. All right. So let's go ahead and get started. So recall that, what does this mean? So this is basically saying the integral of f of x from x equals a to x equals b. And so remember what this actually meant. We had some kind of curve, f of x, over some interval starting at x equals a to x equals b, right? And what we did was we first approximated the area under the curve by using smaller and smaller rectangles, right? And we did this in two ways. We used the left-hand sum approximation by using the left endpoint, and then we used the right-hand sum. And at the end of the day, what we did was, we added up all these areas from these various rectangles that we found, and that gave us an approximate area under the curve. Well, it turns out that we can find an exact area by using properties of derivatives. And so we're going to talk about that a little bit more. But keep in mind that what we're really doing is we're looking at a limit of sums when we talk about integrals, right? We're taking the limit as the rectangles get smaller and smaller and smaller, right? As they get skinnier and skinnier and skinnier. That's the limit that we're looking at as x goes, or as n goes to infinity. If n is, the number of rectangles that you have. And, keep in mind that this right here, this f of x times dx, is really talking, we can think about this dx as a small change in x. And we can think about this as our y value, or since we're thinking about rectangles, we can talk about the height. And so, this makes sense that we're summing up areas of rectangles because the small change in x is just the width of the rectangle. Right, so this is the small change in x, is the width, and the height is going to be f of x, right? So this is going to be, we can say that this is dx, comma, f of dx. Informally, we can say that. And so we're just summing up all of these really, really small areas of rectangles. All right, so that's just kind of a recap on what we did last week. Now let's talk about integrals in terms of real-world functions. And my favorite real-world functions, as you guys have probably guessed, position, velocity, and acceleration. All right. So velocity is distance over time, right? And so our units for velocity are going to be some measure of distance divided by some measure of time, such as meters over seconds. And so the question is, knowing this, what are the units of this integral from 0 to 5 v of t dt? Well, let's think about it. So dt, this is small changes in time. So this is going to be, the units are going to be seconds for dt. And v of t, well, that's going to just be my velocity, right? And my velocity is distance over time. So this is going to be meters per second, right? Now, if we multiply these out, let's do that maybe down here. If we multiply these out, we have meters per second times seconds. And of course, these seconds are going to divide each other out. And so we're left with meters. That's the unit of this integral. And that makes sense, right? Because velocity is the derivative of position. So position is the antiderivative of velocity. So we expect that this should be our units of position, right? Now let's look at what this means graphically. So here is our velocity curve. We have meters per second is our, output. That's going to be on our y-axis, our vertical axis, and our time is going to be on our horizontal axis. And we're integrating, we're trying to figure out what the area under this curve is from t equals 0, so at time 0 to time 5. So what is this curve representing? Let's write this in words, because this is important. So what this is saying this area is telling me the following. Maybe we should write it like this. What this area okay. Guys, I'm not good at English and it's early. All right, so what this area means. This means, so we just established that when we integrate velocity, we get position, right? Meters. Okay, that's a position unit. So what does this mean? So this is the net, or the total distance traveled from 0 seconds to 5 seconds. That's what this area is telling me. All right. Now, if this was, let's say that this wasn't velocity, let's say it was acceleration. And so our units of acceleration is meters, if our time is seconds and our distance is meters, then units for acceleration is meters per second squared. So then the question is, what does that area represent? Well, acceleration is the derivative of velocity. So velocity is the antiderivative of acceleration. So if this were the case, if our picture looked like this, that area would represent the net change in velocity from time equals 0 seconds to time equals 5 seconds. So that's the key idea here. All right. Let's go ahead and change this back. All right. Let's go ahead and move on. So, okay, so again, suppose acceleration, a of t is the acceleration of a particle, and we have distance over time squared for our units for acceleration always at time t seconds. So the question is, what are the units of this? All right, so we're looking at the antiderivative of acceleration. And so if I plug in my units for a of t, that's meters over seconds squared, times the change in time, a small change in time. So what are my units of time? That's going to be seconds, right? Now if we multiply straight across, this is going to give me meters per second. So these are my units here. And notice we have distance over time. So that's going to be velocity that we're finding. And again, you know, we can kind of look at this the same way. We're starting from t equals 0 seconds to t equals 5 seconds, and this area under the acceleration curve. So this area represents the net velocity from t equals 0 seconds to t equals 5 seconds. Okay? All right, so let's go back to the fundamental theorem of calculus. I kind of glossed over it a little bit last week, but since it's called the fundamental theorem of calculus, it's pretty fundamental. So I want to talk about it a little bit more in in this lecture. If you guys stick around for Calc 2, we're going to talk about the second fundamental theorem of calculus next semester, and we're going to do a bunch more of we're going to use some strategies to integrate certain functions that aren't easy to integrate. All right, so here is the fundamental theorem. I'm just going to repeat this. If we have a continuous function on some interval from x equals a to x equals b, and f of t, I'm using t as my variable here, is the derivative of the antiderivative, basically, then the if we're integrating from a to b f of t dt, we simply find the antiderivative of f of t and plug in our upper and lower bounds here. And we did a bunch of these last week, but let's go ahead and just remind ourselves how to do these problems. So here we have a function x squared plus 5x, and what we're interested is the area under the curve from x equals 1 to x equals 3. So let's go ahead and just kind of do a rough sketch of what that parabola might look like. Let's see. So I don't know, maybe it looks like this. And let's see, let's x equals 1, let's do x equals 3. I don't know, somewhere way up here. All right, so here is our parabola. And what we're interested in is we're interested in the area under the parabola from x equals 1 to x equals 3. This is what we're trying to find with this integral. All right, so let's go ahead and do this. The first thing we need to do is we need to find the antiderivative of this thing. And so remember how we did that? We added 1 to the exponent and we divided by whatever we got there. So the antiderivative here is going to be x to the 3 over 3, which, by the way, is, capital F. We use capital F to denote this antiderivative. All right, so plus 5x squared over 2. So this is my antiderivative. And of course plus c, but we don't need to do that with our definite integrals. And actually I should have made this, oh man. Well, I should have made this actually, fine, whatever. Our variable is x here. So this is our antiderivative. And what we're going to do is we're going to now apply this part of the fundamental theorem, which says that I want to take b, which is my upper bound here. This is b, this is a. Plug it in here, so f of b is going to be 3 cubed over 3 plus 5 times 3 squared all over 2. So that's f of b. And f of a, we're plugging in 1 into our antiderivative. So we have 1 cubed over 3 plus 1 squared over 3. Or 2, sorry. Okay. So once we compute this stuff, let's see what I get. Let's see. Okay, I think we end up getting, when we do f of b minus f of a, what this comes out to be when we get a number here and we get a number, when we get a number here, when we get a number here, and we subtract these two, we end up getting 12. All right, so that is how we can apply the fundamental theorem of calculus to evaluate these definite integrals. And 12 is going to be this area right here. That's an area of 12. Okay, so I think there's a problem like this on the homework, which, it could be tricky if you don't read it correctly. So let f of t equal capital F prime of t, where capital F of t, which is the notation for antiderivative, equals 2t cubed minus 4t squared plus 2t. Evaluate the following using the fundamental theorem of calculus. Okay, so what we could really do here is we could replace things if, the whole idea is that we have our antiderivative, and really all we need to do is, plug in our endpoints. Really all we have to do is this. So we're really doing, plugging in 2 into capital F, subtracting off when we plug in -4, and that's gonna give us our answer. If I kind of just used what they tell me and plug it in, we're gonna get the same thing. So f of t is told to be capital F prime of t. So if I take the derivative of this guy, if I take the derivative of that guy, that gives me 6t squared minus 8t plus 2, using the power rule, right? Of course, dt. And what do I do from here? Well, I take the antiderivative to evaluate this, and we know what the antiderivative is. It's this, 2t cubed minus 4t squared, blah, blah, blah. All right? So, we could work it out using our rule, but you'll see that this simplifies to f of t. All right. All right, so all that's left to do is plug in my, my endpoint. So I have 2 of 4 cubed minus 4 times 4 squared plus 2 times 4. So I'm taking that, and I'm subtracting off when I plug in my -2 in for t. All right, and when you do this math, you should get, let's see, I did this ahead of time so we wouldn't be fumbling around with signs and stuff. You should get 204 for your answer here. All right, so that is going to be the area under this curve from x equals -4 to x equals 2. It's 204 units squared. All right, so as I mentioned before, velocity is the derivative of position, and acceleration is the derivative of velocity. So since we learned about antiderivatives, again, antiderivatives are represented with this capital F typically. And so if if lowercase f of t is the velocity function, then the antiderivative, capital F of t, is the position function. And so what we have here, using the fundamental theorem of calculus, is the antiderivative of velocity is position. And so, we can look at this in two ways. We can talk about units. And so velocity, we could say, is distance over time, maybe meters over seconds. And that's times the change in time, which is in seconds. And so my units should be in meters here. But we can also look at it in this way, right? Here I have position at time B, and here I have the position at time A. And this first position is going to be in meters, as well as the second position. So if I'm, if I have some amount of meters and I take away another amount of meters, well, that means that my unit should be in meters, right? So that's another way to look at it here. All right, so let's talk about these. So if f prime of t is f of t, and f of t is the velocity in miles per hour with t in hours, what are the units of this guy and this guy? So here, again, we can just, look at this in terms of plugging in our units and seeing what the multiplication gives us. So f of t is in miles per hour. So we have miles over hour. And the change in time is going to be in hours. Multiplying, we get that our units should be in miles. Another way we can look at it is here. So here, this capital F represents a position function, right? And this in particular is the position at time B minus the position at time A. And we were told that position is in miles, and so we have some amount of miles minus another amount of miles. So this tells us that the units here should also be in miles, which makes sense because, the fundamental theorem of calculus tells us that this is how it should be. Let's do this one. If f of t is measured in dollars per year and t is measured in years, what are the units of this guy? Well, again, I can just plug in my units. F of t is dollars over year, so dollars per year, and the change in time is going to be in years. So crossing that out, my units should be dollars. All right, what does the integral represent? So remember, the antiderivative of acceleration is velocity, right? The units here, if we were to plug in kilometers per hour squared times hours, that is going to give us, our units are kilometers per hour for velocity, which makes sense, distance over time. So this represents the net, the total, let's see, the net change in velocity from, well, we're starting at 0 hours. So maybe we could say from hour 0 to hour 6. Okay, so that's what this integral represents. Now, what about down here? This time we have the integral starting at 2005, ending at 2011. And f of t is the rate at which the world population is growing in year t. So we know time is in years. in billion people per year. So our units for f of t is billion people per year. If we plug that in here, so we have, for f of t, we have billions per year, people, right? Times the change in time. Well, the change in time, that's going to be in years, right? And so this is just going to be in billions of people. So what does this represent? So this integral represents the net population, right, the amount of people from 2005 to 2011. And our units are billions of people. Okay? All right, so let's go ahead and do some examples here using the idea that position is the antiderivative of velocity. Okay, so, all right, so let's see. We have two cars, A and B. They start side by side and accelerate from rest. The figure shows the graphs of their velocity functions. So the first question is, which car is ahead after 1 minute? All right, so how are we going to do this? Well, we're given a velocity versus time graph, right? And so what this means is that we can find the position at any time by looking at the area under the curve, or curves. All right, so let's go ahead. So here's what we're looking at. We're interested in what happens, which car is farther ahead at t equals 1 minute. And so we need to see how much distance they have accumulated. Well, if we look at the area under curve A, I'll represent that with yellow. So the area under curve A is all of this, but it also goes all the way down to the x-axis. So that yellow represents the area under curve A. Now under B is going to be the area that, is made with the B curve and the x-axis. So that's going to be this piece. But, this piece is also part of A's area. And so the idea here is that A has a larger area under the curve. And so it's further ahead. Remember, under the curve is the distance. Because there is more area under A's curve. All right. Okay, so then it says, what is the meaning of the shaded region? Let's go back here. So this blue region that's shaded in, what is the meaning of this shaded region? Well, we can think of this as kind of like area minus area, right? Basically, what we're doing is we're taking the area of A, right? That's it. We're taking away the area of B to give us that shaded region, right? So what does this represent? Well, this represents basically how far ahead A is from B. Okay, so again, this is, you know, the distance that A has covered minus the distance that B has covered. So, you know, we're looking at how far A is ahead from B. All right, and let's look at part C now. In part C, we have which car is ahead after 2 minutes. So this time I'm going to sort of move this to 2 minutes. And now I'm supposed to be comparing the total area under these curves, you know, that's been accumulated. Okay, so let's go ahead and just do A in yellow. So this is the area under A's curve with the x-axis all the way to 2. And we'll do, you know, under B, we have some green here. This is under B. But we also have some green in here. All right. And so the question is really, because this region right here under this purple that I've drawn, this region under the purple, you know, that accounts for the area of A and B. And so really the question is, which is bigger, this little yellow piece or this little green piece? Whichever one's bigger is going to tell us who's ahead after 2 minutes, because, you know, the area under that purple is accounted for A and B. So I don't know. This one's actually kind of hard because it looks like if we were count the squares, I would say this is a tough call, right? Because the regions, this region right here versus this region are very similar in size. So you know what I would say here, because we don't have an exact number of squares that we can count, what I would say is, I would say here that these cars are very close to each other at this point. Because the areas under the curves respectively, are almost the same, right? I mean, it's really hard to tell which one of these, you know, whether or not this guy versus this guy is bigger. It's kind of hard to tell there. Okay, so that was that. So this was this car problem, and this is kind of a classic problem when talking about the relationship between velocity and position. So let's go ahead and look at this problem. There's one kind of similar to this in your homework, so let's just go ahead and do it. All right, so I have two questions. The first one is, what is the total change in position? And the second one is, what is the distance traveled? Now, the graph that we're given is velocity. So I know that position corresponds to the area under the velocity curve. Now, what I can do is I can do one of two things. We have the tools now to set up a definite integral and integrate this thing from t equals 0 to t equals 10 and just figure out what that is. That's going to give us our net change in position. So let's go ahead and do that, actually. So the first thing is like, what is this function? What is this line? How can we write it so that we can integrate it? Well, for a line, all we need is the y-intercept, and that's here, and we need the slope. So if I start here to get here, I have to rise, quote unquote, -4, and I have to run 8, right? And so that's telling me that my slope is -4/8, which is just -1/2, all right? So here's the problem. The function that I'm integrating, I'm starting from t = 0 to t = 10 seconds, right? I want to figure out what the area here and here is going to result, you know, add up to, basically. And my function, my line, is just -1/2 t, right? That's my, like, x value, plus 4. And I'm integrating with respect to time. So that's the problem. Now let's go ahead and do it. So the antiderivative of this, the antiderivative is just going to be -1/4 t squared plus 4t, and we're evaluating from 0 to 10. Now if I plug in 10 for t, this is going to give me 15, right? And if I plug in 0, that's just going to give me 0. So 15 minus 0 is 15. So my answer here, my total change in position is 15. All right. Now that's something different than the total position traveled, right? Let's actually change this so that it matches, which is actually kind of sounds stupid. What is the total position traveled? That doesn't make sense. Let's change it back to distance. But I hope you guys are understanding what I'm trying to say. The change in position is different from how far you actually traveled. And the reason is because we have this negative piece, is like that is being incorporated in the integral calculation. Whereas if we just take the areas of these separately and add them up, that's going to be the total distance. So let's do that. Now, I don't need to, you know, well, whatever. Let's just do this. All right. So, you know, what is messing with the signs is this part where the area starts to go negative right here. Okay. So here it's above the x-axis, and that's fine. So let's go ahead and compute that. So we're going from 0, x = 0, but we're stopping at x = 8, so that our negative calculation doesn't get weird. And again, you know, I had this function that I was integrating with respect to t, and of course we found the antiderivative here. It's -1/4 t squared plus 4t, and we're evaluating from 0 to 8. Now if I plug in 8 in for t, what I'm going to end up getting is 16. All right. Let's put that in our pocket. All right, so that's the area of, let me actually erase some of this. Let's just make this clear. That's this area under this curve. So this is 16 units, I guess, centimeters squared. Or, you know, I mean, let's think about in the context of this problem, how far did it travel from 0 seconds to 8 seconds? Well, our distance is in centimeters, and so this is telling me that from 0 to 8, this thing traveled 16 centimeters, okay? Now, what's happening when it dips below the x-axis? What does that mean physically? Well, what that means is that, you know, it basically means it's the object is turning around, right? Because at that point where it crosses the x-axis, velocity is 0. velocity, and it starts to dip below the x-axis, which tells me that when velocity is negative, it tells me that the object is moving in the opposite direction to where it started from. All right. So let's go ahead and finish this off, because we're interested in the total distance. So far, we know from 0 to 8, it went 16 centimeters. And then we're interested in what happens from 8 to 10 next. Okay, so we have our antiderivative. So we might have to do some more work because we don't have 0 on the bottom here, but that's okay. All right, so let's see. We have negative a fourth times 10 squared plus 4 times 10. We're going to take this answer that we get there, and we're going to subtract off negative 1/4 times 8 squared plus 4 times 8. And let's see what that result should be. So that's going to give us a negative 1. Remember that integrals take, take signs into account, right? And so what does that mean, negative 1 centimeters? Well, all it means is that I traveled 1 centimeter in the opposite direction than when I started, right? So really, we want to look at this. So when we talk about total distance, we discount the negative. So, notice that when I add these two, I get 15, right? And that's what I originally got for the total change in position, right? Because where it started, it started some amount, it traveled 16 centimeters, so like maybe it's an ant, I don't know. Maybe it's an ant. It's a great ant, I know. So, it travels, it goes 16 centimeters, and then it turns around and it goes 1 more centimeter, and it ends up here. And that change relative to where it started is a change of 15 centimeters, if that makes sense. So altogether, this thing really traveled 17 centimeters is what I'm getting at. It went 16 centimeters in the right direction. It went 1 centimeter in the left direction. And altogether, it traveled 17 centimeters. That's our answer there. All right, the graph shown represents the velocity of an object in meters per minute for approximately which t is the object going fastest. And the next question is, what is the significance of t equals 30, and what is the total distance? Okay, so let's take this question by question. Fastest. Remember, okay, negative velocity does not mean it's slowing down, okay? What that means is it's traveling at a speed in the opposite direction. So if I have a car or a ladybug or whatever this is, okay, God, I can't draw. I don't know what is wrong with me. Jeez. Whatever. All right, so we have this truck, right? And here comes the truck going 80 miles per hour. This is a velocity. And he's traveling towards, going towards the east, going towards Texas maybe, because it's a truck. I don't know. I'm just being stupid. He has hay in the back, and he's, going to work on the farm. All right. So now, what does it mean when he's going negative 80 miles per hour? What the heck does that mean? Well, all that means is that he's going the other way. So he's, So he's going the other way. Don't judge me for these bad drawings. So, you know, now he turns around and he's no longer going east. He's going west. He's going towards Tucson or San Diego or something. He still has a lot of hay in the back, but that's okay. So that's what I'm trying to say here is that, you know, velocity, the car is still going the same speed. It's just this negative says it's going in a different direction. Okay, so that's really what I wanted to get at here. So let's go back to this question. What time is the object going fastest? So velocity, this is the velocity graph. So we want to see where is velocity highest. Now, on your homework, I think that for the graph, you know, we wanted to take into account the negative as well, because like for here, you know, this is negative 40 meters per minute. This is, you know, reaches a max height of 60 meters per minute. But I think on your homework, you know, there was something like this. However, it dropped down to negative 70 meters per minute. And let's just pretend for a second that it was actually here and not the lowest point here. Well, if there was a point here on the graph, this would be your answer for part A. That is when A is going the fastest because it's just going 70 meters per minute in a different direction. It's traveling faster than up here. Okay, so I just wanted to make sure that was clear. All right, so when is it going the fastest? Well, right here, right? So it's going fastest from t equals 10 to t equals 15. Yeah, 15 meters. Or sorry, minutes. So t equal from, maybe let's write it like this. So from t equals 10 to t equals 15 minutes. It's going the fastest. Because it has, I mean, that's where it peaks on the velocity curve. But again, you know, if this thing did reach negative 60, you would have two answers, right? Because, you know, the speed is the same, it's just different directions. All right, so part B says, what is the significance of t equals 30? What's happening here? So that's when the velocity is 0 here. So the velocity is 0, but not only that, you know, it starts to dip below the x-axis. The velocity starts you know, becoming negative. And so what does this represent with a car? And again, you know, I know the units are different, but just for the sake of discussion, it looks more like a roller skate, but whatever. Here's our car. He's going down the road. And he's going in one direction from time equals 0 to time equals 30. And then something happens, right? His velocity starts dipping into the negative realm. And so what this is saying is that he turns around, right? This is the point where he turns around and starts going the same speed in the other way. Why is it the same speed? Well, because, you know, the slope is the same, basically. So he's going... So now he's going this way. And he's going this way from t equals 30 all the way to t equals, it looks like this point is 55. Right? Now he doesn't turn around here. Okay, this is a common misconception. what's happening here is, well, you know, he's speeding up, right? Because the velocity is just getting more and more negative, but the value of the number is getting higher, right? So he's speeding up, okay? But then he starts slowing down, all right? So this is the point where he starts slowing down. And, you know, it climbs higher and higher and higher, and then we're at velocity 0 again, all right? So what is the significance? So this is where velocity is 0 and the object turns around. Okay. Now the next question says, what is the total distance? Well, we have to sort of parse this, right? Because, you know, we have this trapezoid right here. We can find the area under it. We have this guy right here, this triangle. We can find the area under it, and we can add up those areas to find the total distance traveled. Now, if this was a different question, if it said, what is the total change in position that the object traveled? Well, if that's the case, we have to make this a quote-unquote negative area to find the total change. But since it's asking for the total distance, we're just adding these areas up, and neither one of them we're counting to be negative. All right, so let's go ahead and do that. Now, the area of a trapezoid, if you recall from last week's lecture, is base plus base over 2 times the height. So if I look at this orange trapezoid, it looks like base 1 is 30. Base 2 is going to be this top part, which is, it just looks like it's 1. No, this is going up by 5. So this guy is going to be 5 units long. All right. So base plus base over 2 times the height. And let's see. The height is going to be 60. Did I do this right? Let's see. Let me just double check. So our base here is 30. Base here is 5. Okay, yeah, I think that's right. Okay, so let's go ahead and do this. We have 35 times, let's see, 35 times 30. It's going to give me 1,050. Now let's go ahead and find the area of the triangle. So area of the triangle is, you know, base times height over 2. So this triangle has a base. We're going from 30 to 45. So it's going to have a base of 15. And a height of 40. Right? Oh, wait, that's not a base of 15. Hang on. Let's see what we got here. 35. Oh, no, maybe that's right. Okay. So, yeah. 5, 10, 15, 20, 25. No, base of 25. Yeah, base of 25. And a height of 40. All right. So we have base times height all over 2. And that is going to give us, let's see what we get. We get 500. And so now we just add up these areas, these two guys. All right, so the total distance traveled is going to be 1,050 plus 500. So this is going to be 1,550. What are our distance units? Meters. All right, so that is the total distance that this object traveled on its trajectory. All right, I'm going to go ahead and stop this video. We'll pick back up on this question. Thanks for watching, guys. A bungee jumper leaps off the starting platform at time t equals 0 and rebounds once during the first 5 seconds. With velocity measured downward for t in seconds and t is between 0 and 5, the jumper's velocity is approximated by the velocity function v of t equals negative 4t squared plus 16t meters per second. So the first question says, how many meters does the jumper travel during the first 5 seconds? So the first thing we need to do is, if we were to just take the integral of this function to find position, the total distance traveled, we're going to find the net position traveled, which doesn't necessarily, so that's just with respect to the starting point. So it might make sense to actually answer question B first. So where is the jumper relative to the starting position? Well, all we have to do is we have to integrate v of t, and we are interested in integrating this guy from t equals 0 to t equals 5. All right, so let's go ahead and do this. Now we need to find the antiderivative of this. So the antiderivative is going to be negative 4/3 t cubed plus 8t squared. And we're evaluating from 0 to 5. Now, if you plug in 5 into t, what we're gonna get is approximately about 33 meters. Okay, so that's our answer here. Again, we're just plugging in 5 for t into that antiderivative minus plug in 0 for t, but that's going to clear out to 0. So, okay, so we've answered that one. And basically, what does this represent in terms of the jump? Well, again, this is just kind of answering question B. This is saying, this is where the jumper is relative to his starting point. Okay. So that's all fine and good, but let's go back to the first question. All right. The first question, we can't just take, the integral like we did for part B. I mean, because, what the integral is taking into account for is quote unquote negative area, right? Now, negative area is just corresponding to a direction. It's really not telling us how far the jumper traveled, right? So think about the bungee jumper. He's on this platform and he's hooked to this cord, and so he jumps, and there comes a certain time in his flight where he actually stops and then goes back up, right? That's how the bungee jump works. And that's when when he goes back up is when the sign is going to start to change, the sign of the area. So what we need to do is we need to figure out the total distance he traveled. We need to figure out this point at which he stops and turns around and goes back up. So the question is, when does he stop and go back up? Because we're changing directions, that's gonna, mess with our signs. That's why what I expect to happen with this calculation is I expect to get a bigger number for the total distance traveled because, I don't know. Actually, maybe we shouldn't assume that, but the point that I'm trying to make here is that when he's down at the bottom of that chord, his velocity is 0, right? Because, he has to stop before going back up. He can't be completely in motion, right? So that's what we need to figure out, when velocity is equal to 0. So let's go ahead and do that. So v of t equals 0, and we're trying to figure out what times that happens. So I have this equation right here, 0 equals negative 4t squared plus 16t. And what we can do is we can factor out a negative 4t. So I get t minus 4 equals 0. And so if I set these factors equal to 0, I've learned some information. I've learned that at 0 seconds, he has 0 velocity, which makes sense because he's just standing there. He's not moving. But also at t equals 4 seconds, he has 0 velocity. So that point in time is going to be 4 seconds, and then he starts going back up. And so what we need to do is we need to sort of parse this interval, right? Because from 0 to 4, he's going one direction, but then from 4 to 5, he's going back up. And so that's going to, in our integral calculation, that's looking like a negative value. So that's what we need to do. We need to parse this thing up. So right here, this is at 4 seconds when he starts to, that's how far he goes down. So let's figure out what this quote-unquote positive distance is going to be. And we can do that using our integral. This time we're starting at time equals 0 to time equals 4. We want to know what he's traveling. So we're integrating this velocity function. And I'm actually going to erase this so I have more room. All right, so we already took the antiderivative in part B. So what this is going to look like is we are doing negative 4/3 t cubed plus 8t squared from 0 to 4. And when I plug this in, I'm getting about 42.7 meters. All right, so let's put that in our back pocket. So let's write that down, actually. So from t equals 0 to t equals 4, he has traveled, going down, jumping. He has traveled 42.7 meters. All right. Now we need to figure out, what he traveled with that remaining, so once he goes back up, right? He goes back up for 1 second. And the question is, what is this distance? What is that distance that he travels in that 1 second from 4 to 5 seconds? So let's go ahead and use our integral again. But this time, we're going to take note that, whenever we get our answer, it should be negative because he's moving upwards instead of downwards, how he started. And so we're going to have to change our answer from negative to positive. Just see what the distance is. All right, so now what we're going to do is, yeah, we have the same antiderivative, but this time we are interested in the distance he traveled from 4 seconds to 5 seconds. Okay, and what we're getting here is, let's see. So we're getting approximately 9 meters. Getting approximately, and by the way, it's going to come out negative, right? But we want to take the absolute value of that when we're talking about total distance changed, or total distance accumulated, rather. So all together, if we add these two up, we're going to get, let's see, so this is about 43, so that's going to give us about 52 meters. So this is our answer for part A. This is the total distance that he went. So again, he's traveled 42.7 meters on the way down. Then he stops, and that thing, the cord throws him back. I guess that's a weird word for it. He throws him back up 9 meters in the opposite direction. And so the total amount of meters that his travel is 52 meters. All right, let's do an example. We have a velocity graph, as we usually do. And we have this particle, something moving along the x-axis, horizontally, basically. It's, we can think about an ant crawling or something like that, or a truck going to Las Cruces or El Paso. And we're interested in what happens. We're not given units, which is annoying, but it's fine. We're interested in what happens from t equals 0. Maybe we're talking about minutes here. To t equals 11 minutes. And so our first question here is, along this interval, looking at this velocity graph, and actually this is probably what I was talking about earlier, when is the speed of the particle the greatest? Well, this is velocity. So, when we talk about speed, we're really taking the absolute value of velocity. Let's write that down here. The absolute value is speed. So we could care less what direction it's moving in. As long as the number itself is bigger, it has a bigger speed. And so that's going to happen here, all right? So the speed here, it looks like the speed, so the velocity is about -6, whatever that may be. I don't know. Let's just say it's meters per second, just to give it some units. And so that tells me that the speed is the absolute value of this, so it's going to be 6 meters per second. All right, so the speed is greatest at t equals 8. All right. Okay, let's look at the next question. At which times t equals 2, t equals 6, or t equals 9 is the acceleration of the particle the greatest? Explain your answer. So here we're given a velocity graph, and remember, acceleration is the derivative of velocity. So what we're interested in is the slopes, right? Where, derivative means we can think about that as slope. So where is the slope the greatest at these, t values? Okay, so let's look at t equals 2. Well, at t equals 2, it looks like acceleration is about 0. That slope looks pretty flat. All right, so with that in mind, let's go to t equals 6. So that's right here. Well, the question is, what is the slope of this line? We can compute that. So let's see. We can compute that, you know, by just using the slope formula, basically. So we have, and this is a straight line, so we can just pick another point on here. So like, I don't know, maybe let's just find the slope of this guy. Well, this point right here is 6, -3. And then this point down here is 8, -6. So using our slope formula, y minus y over x minus x, you know how we do. So there's our slope there. So here we have acceleration is -3/2. All right. Now let's look at our final answer, which was at t equals 9. So we can see that t equals 9 is going to be right here. And now we need to find the slope. We need to find the slope here. Well, again, we can just look at this because, it appears to be a straight line. And again, this was 8, -6. And here we have 9, -3. So let's go ahead and find the slope. We have y minus y over x minus x. And so that is going to give us a positive slope of 3. So this is m equals 3. And so out of all of those, we had acceleration. So at 6, which is right here, acceleration was -3/2. At 2, acceleration was 0. And at 9, acceleration was 3. So here is our answer here. All right. Moving on, the next question says, over what time intervals is the particle moving to the left? Well, we kind of talked about this earlier in the lecture, but let's talk about it again. So, when velocity is positive, that's when the particle is moving towards the right. When velocity is negative, that's when the, sorry, my pen is like doing this weird thing. Sorry. When velocity is negative, it's moving to the left. So, with that being said, if we look at when it dips below the x-axis, this is when the particle is moving towards the left. So from and I should have said at t equals 9 for part 2. But anyway, so from t equals 4 to t equals 10, it's moving towards the left. And what's the reason? Well, the reason is because when velocity is negative, we're indicating a different direction from when we started. So if we call this, the right direction, it starts above the x-axis. Velocity is positive. Velocity is 0 at t equals 4. And then it starts dipping below the x-axis. So at t equals 4, this thing's turning around, and it's moving the other way all the way up until t equals 10. Then it starts, moving in the in the right direction again. Over what time intervals is the speed of the particle decreasing? All right. So again, we're just seeing what happens to the speed. So let's see. So, you know, if we start at t equals 0, well, the velocity is increasing, right? It's getting bigger and bigger and bigger all the way up until t equals 2. And then it starts falling, right? So where does it start falling? It starts to fall from t equals 0. Let's see. Or wait, let's see. Sorry, not t equals 0. It starts to fall at t equals 2 to t equals 4. All right, it starts decreasing there. But then, you know, it's just turning directions, right? So, you know, your velocity is going from 0 to, and the speed is going to 2 to 4. So it's speeding up right here, right? It's, you know, the velocity is getting more negative, but the absolute value of the velocity is not. So the speed is, you know, it's still gaining speed all the way up until this point right here. And then it starts getting less and less negative, and finally the velocity is 0 again. All right. So here, another place where it's decreasing is from t equals 8 to t equals 10. And then it starts increasing again because we're at velocity is 0 right here, and then the velocity is increasing. All right, so last question, find the total distance traveled by the particle over this entire interval. Well, again, we want to kind of parse this up. Now, we don't have a function for this, so it doesn't make sense to use an integral here. We can kind of do this the old-fashioned way, how we started with these area problems. We want to take the area of this piece right here, add up the area of this piece, and finally add up the area of this little skinny triangle right here. So the area of the semicircle is going to be pi r squared over 2. Now r is going to be, in this case, is going to be 2. So we have pi 2 squared over 2, which is just going to reduce to 2 pi. Now the area of that yellow triangle, base times height over 2. Well, the base is 6. The height is also 6, as we can see here. So base times height over 2, and that's going to give us 18. And finally, the skinny triangle, we have our base is 1 from 10 to 11. Our height is going to be 3. So we have base times height over 2. So that's about 1.5, right? Now, for the total distance traveled, all we have to do is add up these areas. So we have 2 pi plus 18 plus 1.5. And I'm not going to, you know, write this as a decimal, but this is the total area under the curve, and hence the total distance traveled by the particle over that time interval t equals 0 to t equals 11. So I hope this video was helpful for you guys, and thanks for watching.